All right, section 7.2, we're going to be talking about properties of exponential functions. So if you think about the exponential function y equals ab to the x power, the a value in that particular expression, so here, is going to cause a stretch or compression of the original exponential function. It can also then cause you to reflect across the x-axis if it is in fact a negative a value. It just depends on what we're looking at. And so here we have an example of an exponential function. We have our original, and then we have the one here where it is stretched. And so in this case, the red is the original, and then the blue is the one where you have the 3 being stretched by a factor of 3. All right, so this goes back to things we've already talked about in previous chapters. We're going to be using the graphing calculator to help us find some of these values, and then graph and compare the different changes that take place. So in our first example, it says, how does the graph of y equals negative 1/3 times 3 to the x power compare to the graph of the parent function? So what we want to do is we want to create a table of values for one, our parent function for this particular exponential, and then the one where we see it compressed by the negative 1/3. So we're just going to fill this in. So you can type this in your calculator, fill in your values, and get your values accordingly. So now that we have our table set, we have our values, what we're going to do is we're going to plot the various ordered pairs to get an idea of what our two graphs are going to do. So we'll start by plotting the parent function. So this one we have this exponential function getting ever close to the x-axis, and then it increases as it goes to the right. And so there is the y equals 3x. Now we want to graph y equals negative 1/3 times 3 to the x power, or our transformed equation here. Oh, put that one in the wrong spot. There we go. So we see that our transformed here in yellow, or sorry, in purple, not yellow, is flipped over the x-axis. So it asks, how do they compare? Well, one of the things we should note right off the bat is that y equals negative 1/3 times 3 to the x is flipped across the x-axis, and it's compressed by a factor of 1/3. The second problem asks us to do the same thing. It says, how does the graph of negative 0.5 times 5 to the x power compare to the graph of the parent function? So what we want to do is we want to complete a table of values, and then we want to graph the two items and then talk about how they compare. So I'll give you a second, pause, see if you can graph the two of these and see if you can tell how they compare. So once we have our table completed, we see our values from negative 2 to 2 for x, and they vary between the two equations. For your parent function, you're seeing an increase from left to right, but then for the y, in this case, y equals negative 0.5 times 5 to the x power, we're seeing that it's flipped across the x-axis again. And then once again, we see a compression by a factor of 1/2. Or 0.5 in this case. All right, so this is very similar stuff we've done before. The only difference here is now we're dealing with exponential graphs. All right, moving on. A horizontal shift, y equals ab raised to the x minus h power, is the same as a vertical stretch or compression, such that y equals ab times negative h, where b times the x, b to the x power. A vertical shift, in this case, y equals ab to the x plus k, also shifts the horizontal asymptote from y equals 0 to y equals k. So in reality, all they're saying is that when it's written like this, if you have an h value in here impacting, so you have a value impacting your x, that is your exponent, this is going to be a horizontal shift. And we're going to be able to see that shift just like we would anything else, where if it's addition, you're going left, if it's subtraction, you're going right, things like that. A vertical shift is when you have a constant or an additional value outside of the actual exponential piece. And while it's not only moving it up and down, it's also adjusting the horizontal asymptote. And remember, that's the line that this graph will get infinitely close to but never cross. All right, so let's just look at this first example. It says, how does the graph of each function compare to the graph of its parent function? And so here we've got this lovely equation, y equals 2 to x minus 4 power. And so the first thing we want to do is we want to complete our table in this case, just for the parent function, just for the original. Just create a table here, and then we'll do the transformation based on that particular move here. So at negative 2 for this, we get 1/4. Oops, positive 1/4. I don't know where a negative 1/4 there. So we get 1/4. For negative 1, we're going to get 1/2. For 0, we get 1. For 1, we get 2. For 2, we get 4. For 3, we get 8. So this is going to give us our parent function graph. If we wanted to, we could sketch this graph really quick. So we got a graph here, 2, 2, or 1, 2. There we go, 2, 4. And 3, 8 is up here. Oop, 1 too far. So our graph looks like this. In this case, we have our horizontal asymptote at, in this case, y equals 0. And so there's our parent function. All right, so this is the y equals 2 to the x. So now what we want to do is we want to graph our translated value. Well, in this case, this minus 4 here tells us we're going to move this. We're going to translate our graph 4 to the right. So our actual value, if we move every point 4 to the right, our graph now looks like this. And so still has the same horizontal asymptote, but we've just moved it over. All right, and so how do they compare? Well, we should know right off the bat. It's shifted 4 right. And our asymptote is still y equals 0. All right, so here we're doing the same thing. We've got our parent function, or in terms of what we're looking at, just the normal exponential, but then we have to apply this vertical shift. And we should recognize that this vertical shift, being plus 10, means we're going to move up 10 units. So let's just start by getting our values here, complete our table, and see what we get from there. So we got 40, 20, 10, oops, 5, there we go, got to write better, there we go, 10, 5, we can go here, 3 is 2.5, negative 2, y, oh, gotta scroll up, and this should be 80, there we go. So we go from 80, 40, 20, 10, 5, 2.5. So now we can kind of graph this parent function if we want. So this is way up here off the graph, at the 0 off the graph, and then 1 is 10, so it's right here. So our particular graph here, not the greatest, but in reality, this graph is not going to work the way we want it to. So what we're going to do is we're going to change this. All right. Okay, so we'll redraw this real quick. So let's just assume we're counting by tens then. 10, 20, we'll say 30, 40, 50, and 60. All right, and so across the bottom, we can still just go by 1. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so here we go. So parent function wise, -2 is at 80. I'm not going to be able to get hits on there. -1 at 40, so we can get that. It's going to be right here. 0, 20. We'll go here. 110. Good. 2.5. Cool. 3, 2.5. So our graph of our parent function, we'll do this in orange. It's going to look something like this. And then we want to make sure, in this case, it says for our transformation, we're shifting it up 10. So that means if this is y equals 20 times 1/2 to the x power, if we shift all of these points up 10, so like here, this goes up here, this goes up here, this goes up 1, there we go, this goes up here, and then here. We're shifting up 10, and remember, we scaled this graph differently. The other one wouldn't fit. So our graph looks like this. And it's not super accurate. So y equals 20 times 1/2 to the x power. But the big comparison piece that you're trying to get across here is, how are these different? Well, y equals 20 to the 1/2 to the x power, and in this case, it has plus 10. Is shifted up 10 from the parent function, but at the same time, our horizontal asymptote is now moved as well. Meaning that this graph is never going to cross y equals 10. My graph isn't super accurate here, so it should flatten out a little better, where the other asymptote of the parent function was y equals 0. So that's the big difference here. We've shifted up the graph, so we've also moved the asymptote. All right, some things to keep in mind here. We have a concept summary where families of exponential functions. This is just a reiteration of things we just saw. Your parent function, y equals b to the x power. You have your stretch or compression based on your a value. You also have your reflection over the x-axis, when in this case a is equal to a negative number. Or in this case, -1, or a negative number. Translations, horizontal, you see this is the h value. If it's addition, you're moving to the left. If it's subtraction, you move right. And then here, you've got your vertical is the k, addition is up, subtraction is down. And so here, I guess we can say addition is left, subtraction is right. And so these are a lot of our similar transformation rules, nothing really big here. But the big idea is, for vertical though, keep in mind, k moves your horizontal asymptote. So here we want to use this information, and we're going to solve this problem using an exponential model. It says the best temperature to brew coffee is between 195 degrees Fahrenheit and 205 degrees Fahrenheit. Coffee is cool enough to drink at 185 degrees Fahrenheit. The table shows the temperature readings for a sample cup of coffee. How long does it take for a cup of coffee to be cool enough to drink? Use an exponential model. And so when it asks for us to use an exponential model, what we're going to do is we're going to use our stat menu on our calculator to run a exponential regression. So what we're going to do is we're going to put time in the L1 list and temp in the L2 list. And then once we have those lists set up, we're going to run an exponential regression, so that way we get an exponential model for this. When you run this model, your calculator is going to tell you, it's going to give you your equation back in this format. A times b to the x, and it's going to tell you that your a value in this case is, let's say 134 point, we'll say 5.2, we'll just round to 5.2. We'll just round it to 5. I don't want to deal with the extra decimals. And then your b value, in this case, is going to be let's say 0.9, we'll use 0.956. This one will have a little bit more decimals because it's primarily just a decimal. And so what this means is your model for this is going to be y equals 134.5 times 0.956 to the x power. So this is our exponential model for this information. And it says it's best to be drunk, it's cool enough to be drunk when it's 185 degrees. But here's the thing, before we can finalize this final answer, I want you to think about something. This original exponential function here has a horizontal asymptote. Its horizontal asymptote, if you graph it, you're going to notice is that y equals 0, meaning it's the x-axis, meaning that they're assuming this coffee is going to bottom out and be 0 degrees at some point. Well, I don't think the coffee is ever going to really be 0 degrees. The only way it's going to reach that is if you put it in a fridge or a freezer. In reality, this coffee can only ever really get as cold as room temperature. So room temperature, let's say room temperature on average is 68 degrees. So what we want to do is we want to incorporate this into this equation. So that way we shift up that horizontal asymptote so that way 68 degrees is our baseline. So we're just going to add it in. Y equals 134.5.956 to the x power plus the 68 degrees for the horizontal asymptote, or in this case, room temperature. So now we've adjusted it. So now we're accounting for the fact that this data really will never get to 0. It'll get to room temperature. And so this is going to help change our model. But then the question asks, how long does it take before your coffee is cold enough to drink? So what you're going to do is you're going to put this equation into your calculator, and you want to look at the table, and you're essentially looking for the point where you see your y value equal to 185 degrees, or somewhere in that range. So on your graphing calculator, you're going to put this on the y1 line, this part, and you're going to look at the table. When you put this in your graphing calculator, you're going to have to adjust your table set, because as you notice, there's going to be a jump from, at 3, it's going to say 185.53, but that's not exactly 185. And then it jumps to 4. It jumps to 4, which is 180.35. So there's a big gap there. You can't get the exact when it gets to 185. So if you change by going second window and change your rate of change on your window to 0.1, then you can start seeing these other values. And you're going to see that right around 3.1 here, it's really, really close to 185. So after about 3.1 minutes, you're seeing that this coffee should be cool enough to drink. While your calculator is still looking at that table, it says, how long does it take the coffee to reach a temperature of 100 degrees? So looking at the table, you can keep scrolling till you see 100 degrees, and it should tell you at right around 31.9 minutes. Dun, 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 dun. All right. So here, up to this point, we have worked with rational bases, but there's going to come a time where we need to mess with exponential functions that have irrational bases as well. One of the most important irrational bases is the number e. All right, and so we can use e on our calculator. It's actually one of the values that you can plug in. If you look, one of the ways to type it in, if you're curious, is pressing the second key and then the division symbol should bring up the E on your TI-84 calculator. All right, and so we're going to be using this more as we start working with logarithms and things like that, but we just wanted you to be aware of where it is. All right, so take a minute, you can take all this in, but I want to answer this question here is, e to the third power, how do we use our graphing calculator to do this? Well, we're going to press the second key, then the division symbol, which is going to take us to the E, and then we'll just raise this to the third power. So second division of caret third power, and we should get, this is going to equal 20.0, let's say 09. All right, so now we're talking about continuously compounded interest, where in this case you're given the equation A of t in this case, equals P, which is your principal value, times e to the r, which is your interest rate annually, times the t power. All right, so in this case, this is your principal, or sorry, this is your amount in the account at the time t. This is your principal, basically where you start. You have your e, and then you have interest rate. And so in this case, we're going to represent the interest rate there, and then t is time in years. All right, so this is continuously compounded interest. So in this question, it says, suppose you won a contest at the start of 5th grade that deposited $3,000 in an account that pays 5% annual interest compounded continuously. All right, so we're going to use this continuously compounded interest equation. Here we go, continuously compounded interest equation, okay? How much will you have in your account when you enter high school 4 years later? All right, so we have time t is 4. We know our rate in this case is 5%, so the rate in this case 0.05, because we're going to turn it into a decimal. And then our principal is going to be 3,000. So we're going to plug all of this into this equation. So we've got the amount equals 3,000 times e to the 0.05 times 4 power. All right, we can simplify some things here. We've got 3,000 times e, and then 0.05 times 4 is going to give us 0.2. We're going to put this in our calculator, let our calculator handle this, and we're going to get right around $3,664 is what we're looking at in the account when you enter high school. Then it asks how much will be in the account after 4 years of high school. So we're looking at adding an additional 4 years. So we then go into the same idea. We've got the exact same equation, then E, except this time we keep the same rate, 0.05, but our time in this case changes. And then this is times 8. And so we can simplify this down, 3,000 e to the 0.4 power. And when all is said and done, after your 4 years of high school, so essentially 8 years later, you should have right around $4,475 in the account.